Hi everyone, thank you very much. Let me introduce myself. My name is Kabul Kurniawan. Today I will be talking about our research paper titled Cross-Platform File System Activities Monitoring Forensic as Semantic Approach. Why is this important? As you see at those websites that nicely visualize the recent incidents of cybersecurity issues has given a pain for the responsible security analysts to deal with. As you see at the statistic, the number of data breaches have been on the rise in recent years. Data breaches exposed about 431 billion records in the first half of 2019 by Horizon, and it costs about 3.86 million US dollars average total cost in 2020. Furthermore, current attacks have been developed into more sophisticated tactics and techniques makes exfiltration of sensitive data is often difficult to detect. For example, it requires about 280 days average time to identify and contain a breach. These become an existential threats that severely impact organization. For example, in terms of privacy loss, decreased trustworthiness, reputational damages, and direct consequences that affect their bottom line. When illegal fees either due to contractual obligation or laws and regulations, for example GDPR in the EU, that also become critical risk. In general, we categorize adversary into two types here. First, insider with legitimate access to data, either purposely or accidentally exploited data, and also the external attacker that has obtained access illegitimately to infiltrate the organization network and obtain access to the data by spreading malware, spyware, stealing credential, brute forcing password, and etc. So the thing is that such activity typically leave traces in the network and on the involved system, which can be used to spot potential misuse in real time or to reconstruct and document the sequence of events associated with the exploitation. But the challenge is that, for example, the log data that can provide clues of attack indicator, they are typically dispersed, heterogeneous, and in a high volume. And also it requires additional information which is not included in the log files. For example, cybersecurity information that provide uh, helpful information in terms of to contain attack or enable insight. However, they are varied dispersed. Which are mostly published in text, and also ICT asset information that are helpful as it can provide context, and also the limitation of current analytic tools. For example, the SIM, they don't really solve the real problems. They are mostly rely on simple regular expression and statistical analysis with a complex hand craft query, and without a proper context it will produce high false positive result. So basically, manually searching log data and comparing related information to understand attack or event change is tedious and time-consuming process. Another obvious challenge that we face in the log data is log data heterogeneity. As showing in the picture, there are various heterogeneity of log data, including syntactic heterogeneity, means that there are differences in the representation format of data. For example, here we have a timestamp. And also semantic heterogeneity means that there are different meaning and interpretation of data value. And it also has an inconsistent identifier, means that there are different standards to identify data, such as hostname, IP address, and etc. So basically, connecting different heterogeneous log data is hard. It strongly depends highly on the context. The interpretation of log data is also difficult because it requires extensive background knowledge. So there are several approaches proposed by some researchers. File activity monitoring here, statistical analysis to characterize legitimate file access patterns and compare those to file access patterns of recent activities to identify anomalies and data detected by the exploited insiders. And also there are a policy-based operating system costs provenance for data leakage detections by tracking operation performed on sensitive files, and also approach that leverage the data provenance information from OS kernels messages to detect exfiltration of data returned to users from a database, and also have a deep learning model to predict the insider threats. And for file system ontology and semantic approaches, some researchers provide or propose ontology such as TripFS, which is a file exploration framework based on linked data using an FO ontology, and also file poop NFT, similar to TripFS, which focus on end users or user-defined content metadata. Semantic file system or SFS extension to TripFS, but enable users to navigate the published files. And for the file monitoring tools, there are several commercial tools such as SolarWinds, Manage Engine Data Security Plus, File Insights, Tailbits, File Activity Monitor, and Decision File Audit. For the SIEMs, there are LogDNA, Splunk, Elasticsearch, and etc. So we have the research gap here. So most of the current state of the art mainly focus on regular expression, rule-based classification, anomaly detection, and also statistical log analysis. It also lacks of interoperability and contextualization and linking to cybersecurity information. And the existing file monitoring tools provide simple alerting upon a suspicious activity, and the existing SIEMs do not specifically tackle the problem of file activity tracking. So here we leverage semantic web technology that provides several functionalities such as graph-based representation, explicit semantic decentralization, and standard-based query. Here, this feature or this functionality could be a potential solution for the security domain. So, for example, graph-based representation could be a flexible schema for unstructured or semi-structured log data, for example, XML, JSON, CSV, and etc. And also the semantic integration of heterogeneous security-related data, such as WinLog, LinLog, audit log, and etc. And for the contextualization and linking to external and external background knowledge, such as IT assets, cybersecurity information, and also stream reasoning over the security-related data. For example, here for real-time file activity monitoring and also standard query language for log analysis and forensic. And this potential solution could be used to address the current gaps in file activity monitoring and a forensic approach. Here we propose approach. There are three main steps. First is a conceptual modeling. Here we define the conceptualization and model for the log source and security information. So for example, here we develop a vocabulary or ontology and background knowledge. And the second is a semantic log processing. Here we develop an architecture and technique for semantic log processing, log acquisition and execution, log transformation, IDF mapping, evaluation and linking, and also for the semantic log monitoring and analysis. Here we develop the method and mechanism to conduct log monitoring and analysis. So for example, here we leverage continuous querying for log monitoring and semantic query federation for log analysis. We followed a bottom-up approach, starting from the low-level information from the log sources with the goal to choose and collect the appropriate terms directly from the source of evidence, such as users, hosts, files, and etc. And on the low level, we develop or we define a vocabulary or ontology to represent information on micro-level operation for both Windows and Linux log sources. And on the high level file operation event, we model a generic vocabulary to express higher level events, such as created, modified, copied, rename, and delete event derived from the low level event. And in the end, we will have a high level event as an output. Okay, so how about the conceptual modeling for the vocabulary? So this is the vocabularies look like. So we distinguish the ontology for log from Windows and log from Linux because it has a different structure. But in the end, we will have a high level of vocabulary or ontology which represent uh, the structure of file access. So for example, here we have a file access class which has file class that has a hash source file and hash target file, and also a program that represent the relationship between the program that has been run, and also the host, which has the host source, and also the target host represent the relation between the uh, the uh, the current host and also the former host, and also we represent the users for file access who have an action of the user, and the action itself is a type of action that has been happened in the file. So for example, there are created, modified file, and etc. So this is our proposed architecture for semantic log processing of file access events. Here we have the approach for the log acquisition and extraction of low-level data from heterogeneous log sources and hosts, and also realization and event extraction, which is also includes vocabulary and also background knowledge, and log monitoring and forensic analysis and visualization. I will explain for each component more detail in the next slide. Start with the log acquisition. So log acquisition and extraction is a process to ship raw log data from the monitoring host, and using extraction pattern or regular expression, we can extract this unstructured or semi-structured raw log data into a structured representation of JSON. Here we have an example. So for example, here we have raw log data. Using the regular expression, we could generate the structure version of the log data in a JSON. So for example, here we have a timestamp, we have a host, we have a program, we have a PID, we have a message, and so on and so forth. And after having the acquisition and extraction, here we have the collection of structured low-level log data in JSON format. So basically, we identify 5 main file operation or file activity that are exist in the low-level log data, such as created event, modified event, copied event, rename event, delete event, and so on. And in the next slide, I will show you how could we extract this high-level file operation. But before we go there, we have IDF mapping. IDF mapping is a process to transform the accessed log data into machine understandable formats such as IDF by using IDF mapping language. We can map the structural log data with the respected log vocabulary and produce the log graph or IDF. Here we have an example. We have the extracted log data as a JSON, as I mentioned before. After having the IDF mapping, we generate the graph or RDF representation of the log data. On this mapping, we can also perform enrichment, which is to attach the additional information which is not exist or not provided on the original raw log data. So for the high level event extraction, um, high-level event extraction is a process to generate the high-level events from the low-level event log data. This is the example of a mechanism to construct the event in a streaming mode using Sparkle construct query. Using construct query, we can get, for example, the rename event by looking at the low-level log entry, indicate that there are move event and also create event of a file. We could also use some rules. For example, for rename event activity, the current file name should be not the same with the former file name, and it should have the same host. For file access activity visualization, after we have the generated IDF file for access event, we materialize them into a connected IDF graph and visualize them into a file activity lifecycle. So here we have the sequence of file access event based on the file access activity, for example, modified and copied, renamed, deleted, and etc. So for the implementation, we use several state-of-the-art technology to implement our approach. We deploy our system into a virtual environment using Docker. We use WinLogPit and AuditPit to collect the raw log data from hosts and ship them into log extractor component. We use Logstash to extract the raw log data into structured log data as a JSONs and ship them into a IDF mapping component. We use triple wave to map the extracted log stream into RDF graph streamingly, and we use also csprite IDF stream engine and also Jena to process and continuously querying the IDF stream to extract the high level event. And we use a virtuoso triple store to extract RDF data into further log analysis, and also we develop visualization for that. Okay, to evaluate or demonstrate the approach, we develop a scenario depicted in use case 1. So for the scenario here, we simulate a multiple hosts with different operating system as a workstation and one file based on a Linux that store an organization sensitive file. Here we assume that a file has been exfiltrated and the forensic investigation start. We want to find out what happened to this file and how it got exfiltrated. We assume the log file still exists and have not been tampered with. Here we use SparkL query and start with the detected file, namely ctscp001xls in the query and create the file history from there. Using property path related to star, we could automatically generate the sequence of the file activity events of that file. As shown in the result, the file has been manipulated. So, for example, modified, copied, renamed, deleted, etc. The file also has been transferred out to another workstation. So, for example, the Windows workstation and has been manipulated afterwards. The file activity graph nicely visualizes of what happened to the file in both file server and workstation. Okay, so how about the use case 2? The use case 2 is about a log monitoring. Here we want to monitor which sensitive file that has been moved to a vulnerable host. Here we also show that we can include a background knowledge information in those query directly, for example, information on CVE, KPEG, etc., and in link data representation to identify which hosts that are potentially vulnerable according to the current system state, for example, software installed, a running program, and etc. There could be a policy that the sensitive file should not be reside on host which is vulnerable. So using SparkL continuous query or csprite, we register the stream engine to monitor the file access event. We include both internal background knowledge and external background knowledge or cybersecurity information. And as a result, with this query federation, we can get the information out of the file that has been moved to one host to another host. For example, there is a file that has been moved to workstation 2 and turns out that this host has vulnerable information such as CVE ID with an impact score of 9.3. So for the evaluation setup, we use csprite as an event extraction engine with 3-second time window that slides every second. We develop a Java-based event generator to generate script for random file activities and use weighted random choice algorithm to select activities. We report the average time over 5 runs for each experiment, and then we get the detection rates by dividing return events, which is a number of events that's correctly detected, by actual events generated is a number of the events executed in the simulation as a ground truth. So the result is as shown in the figure. In Linux, all events can be detected close to 100% for all frequency, 1 event per second up to 200 events per second, except the copy event, which reached the maximum of 91.89%, which is mainly caused by incorrect pairings of read attributes and create events when this micro operation generated by 2 or more sequential copy events appear together in the same window. And for Windows, the event detection performance for create, modify, rename, and delete event is higher, with almost 100% of detected events for all frequency. However, the copy event detection in Windows Archive achieve a lower detection with a maximum of 75.46%. So for the conclusion, we tackled current challenge in file activity monitoring and analysis, such as the lack of interoperability, contextualization, and uniform querying capability by means of architecture based on semantic web technology. We introduced a set of vocabulary, and then we implement a prototype, illustrate how this prototype can monitor file system activity, trace file lifecycle, and enrich them with information to understand their context. We demonstrate the applicability of approach into scenario in virtual environment. The results of our evaluation indicate that the approach can effectively extract and link micro-level operation of multiple operating systems and consolidate them in an integrated stream of a semantic explicit file activity. That's it, and thank you.